So now we're talking about cells, so it officially feels like biology class.
Yay, phospholipids.
I agree. I think it's pretty cool too.
Stuff and stuff. Stuff is made out of stuff. That's the secret going.
All right. So we kind of start in the cells unit. We kind of start at the edge and look at like the cell membrane and do all the cell transport stuff. That's chapter 5. Then we go back to chapter 4 and we do all the organelles like the nucleus and mitochondria and ER and stuff. The cell membrane is, as far as like the AP Bio test, that's the more important part. So out of chapter 5 and chapter 4, what would help you the most on an AP Bio exam? Chapter 5, membranes and transport, osmosis, diffusion. So kind of the first half of this unit. The second half of this unit, they don't ask nearly as much. Most students prefer the stuff in the second half because it's a little bit easier and it's a little bit easier to visualize. But the chapter 5 is the more important stuff. In science research, chapter 5 is the more important stuff. And to me, they're both really cool. Okay, so to start off, there's just we'll be kind of at the top of those notes where it says phospholipids. I might not go in exactly that order, but I'll be bouncing around in those top like 2 inches of our notes. So first off, what was this right here again? Yeah, it was an unsaturated fat. How do I know that it's unsaturated? Yeah, it's got a double bond and a kink down at the bottom. I know, you never know, like, what somebody feel like, oh, that's what that person looks like. Thanks, Jonah. So I've got a double bond in here. All right, so that's an unsaturated fat. How many tails does that unsaturated fat have? 3. So how do I make a phospholipid?
It's like a lipid with a tail.
Yeah, like a lipid with a tail. How many tails? 2. Because otherwise, didn't your teacher usually draw phospholipids like this? Okay, so it's a lipid with 2 tails. This is a lipid with how many tails? 3. So to make a phospholipid, we cut off one of the tails and replace it with a phosphate. And that's how you make a phospholipid. So I'll take something like this. Switch camera angles. So I'll take something like a glycerol. And it'll be a triglyceride. So I'll have like a tail like that maybe. And I'll have a tail like this, a tail that's saturated. Then I'll have a tail that's got some double bonds in it. Like that. And to make a phospholipid, all I do is I cut off one of the tails. So like if this thing was stable and glycerol had a bond right there, if I cut off this bond, it's now unstable, so it needs another bond. So what I do is I just add a phosphate to it on the other side. PO4. And that's a phospholipid. So we take fat and we turn it into phospholipids. Okay, speaking of phospholipids, let me grab something from across the hall really quick. My audio might cut out in a second because I'm going into the lab, so apologies. All right. We have some vegetable oil. Best diffused by September 13th, 2014. It's a good vintage. I would not cook anything in this. It is a great value. Hopefully it's not super stank. Not to be confused with Hoobastank. That's a band. Yeah. They were not wildly successful, probably because of their name. So here's some cooking oil. And if I'm looking at phospholipids, this is not phospholipids, but it is oil. So what we want to do is if I add water to it, is the oil going to mix very well with the water? No. Nope. So they're going to stay separate. And whoever's more dense is going to be on the bottom. Whoever's less dense will be on the top. Oils are typically less dense. So oils typically float on top of water. Okay. Hold that thought for a second. You're like, you went across the hall to show us this, Mr. Cotton. So hang tight. Okay, so now I've got an unsaturated fat. I rip off a tail, and now I have a phospholipid. I have a phosphate. Most phospholipids usually have one straight tail and one kind of kinked tail. Okay, so lipids. Are lipids typically polar or nonpolar? Nonpolar. What about phosphate? Polar. You're like, well, certainly it's the opposite, the way that he said it. You might have learned in chemistry, phosphate is usually PO4 3- charge. It's got a -3 charge. So phospholipids, are they polar or nonpolar?
Some both.
Yeah, they're both. And so they actually have a word for that.
Bipolar.
That makes sense, but that is very different. But it does make sense, like the name bipolar would work. They call it amphipathic. That word is written in your notes somewhere. But ampha and the PH sound is, the F is actually a PH. The F sound is a PH. A-M-P-H-I-P-A-T-H-I-C. Amphipathic. Amphipathic means that something is polar and nonpolar. So one part of it might be polar, the other part might be nonpolar.
So like stuff sticks to one side of it.
Exactly. And it is a common theme of like what kind of crap sticks to what other kind of crap. It seems like that's 25% of every conversation in this class is like, does this crap repel or does this crap stick to this other crap? So amphipathic. Okay, so now your teacher drew phospholipids like this. What is that straight line right there? A saturated fat. What's that kinked line right there? An unsaturated. So your teacher basically just took this picture and went, hey, I'm going to do this. And that's a phospholipid.
It looks like an LED.
It does kind of. Like in the little physics when you guys do all those circuits and stuff in physics class and they have the little bulbs. Yeah. So that's a phospholipid. The round part is representing the phosphate, and those represent the lipid tails. So which part is polar, the round part or the tail part? The round part, polar. The tail part, nonpolar, yeah. Okay. So now, let's say, I'm going to erase just this part. So let's say that I've got a cup of water. So this is water. And I have a cup of phospholipids. Got on sale. So here's my cup of phospholipids. And I dump the phospholipids onto the top of the water. What will they look like? Well, they look like you've got a few different options. Will they look like this? 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 Or that. So I have A, B, C, D. Or if it's in Canvas, That one, that one, that one, and that one.
That one at the one place with the...
So, A, B, C, or D? So, how many of y'all think it's A? How many of y'all think it's B? B wins in a landslide. It's B.
You know what's funny, Mr. Cotton?
Huh.
I had this really good, biology teacher freshman year, and I learned that.
I did not learn that freshman year.
I didn't have a good biology teacher.
I feel like I've learned it before because I feel like I remember it.
Well, the thing is when I start drawing phospholipid bilayers, that will be familiar. Your teacher might not have gone into why they form that way. But the polar and nonpolar thing you did in all classes, pre-P, on level, doesn't matter who your teacher was. Some teachers go into, I was the very lecture-y ninth grade teacher. So I always tried to explain or over-explain stuff.
People also said you were the
So,
best one, so
do what?
people said you were the best biologist.
Ah, well, thank you. I appreciate that.
That was a disaster.
Here's a quick aside.
Like, you were the lesser of all the evils, I should say.
So I was still evil, but I was the least evil. Yeah. He's trying to back down. I still need to be cool. I mean, come on. So it depends on who you ask. Of my current pre-AP bio students, there are some that hate me. They're like, could you just give us worksheets? And I'm like, no, that's what's wrong with America. And then eventually they'll kind of leave the class and they'll go find something else. Yeah, so generally students that take AP bio are kind of more into that. So it's a skewed crowd, you know what I mean? So, see ya. Thanks for spraying down the desks as always. So anyway, they will orient like this. So let's say, why won't this work? Yeah, water's polar. Non-polar tails don't want to touch water. Non-polar tails don't want to touch water. Here, the non-polar tails still want to be as far away from water as possible. And if something's polar, not only is it tolerant of water, it wants to be with water. So it's not just that polar things are okay being next to each other, they embrace each other. So you might have heard the terms hydrophilic and hydrophobic. Hydro is water. What would hydrophobic be? Fearing. So oil and water. Oil is hydrophobic, it fears water. If something's hydrophilic, philic or philia means to love. So, yeah. Okay, so now, let's say I've got this jar of phospholipids. And this will be cooling a little bit. Hopefully you guys learn along the ways that normally in bio, we kind of learn some stuff, and then in the end there's this payoff where you're like, that's kind of cool. Now I understand something. So if I dump a bunch of phospholipids in there, it'll look like this. All the polar heads will be in the water, because water's polar, and the heads are polar. All the tails are like this. Now, just for some fun phospholipid trivia, because who doesn't like some good phospholipid trivia, there's a bunch of different kinds of phospholipids. So if you're reading in textbooks or they talk about something like a sphingolipid or whatever, there's a bunch of different versions. What they all have in common is lipid tails and a phosphate head. They might have other crap attached on there, but what they have as a base in common is lipid tails and a phosphate head. Most phospholipids technically have one saturated tail and one unsaturated tail.
So why does the phosphate attach to the glycerol?
Because we bonded it there covalently. So it's almost like Jonah's question, if you didn't hear it, was why does the phosphate even bond to these? Because what he's getting at is if this is polar and this is nonpolar, they wouldn't want to be next to each other. And I would say it's kind of like this. If I've got magnets, north pole is the cap, north pole is the cap. If I go like this, they repel. But if I have glue strong enough, I just glue them together, and it doesn't matter that they're still actively repelling, but the glue is stronger. So there's an enzyme that builds phospholipids. And when it does, it bonds them together, and the strength of that bond is stronger than them avoiding each other. So good question. Does that answer your question? Okay, so I've got a layer of phospholipids. Now let's say I go back to the jar of phospholipids. I dump them on there. Now which way do they face? Do they face like this? Or like that. So we have A or B. So how many of y'all think that it's A? How many of y'all think that it's B? Nobody. Okay, so it's A. Why? That phosphate head doesn't want to be next to those tails. Like, all right, Mr. Cotton, this is pretty easy so far. Now I'm just going to get lazy. Actually, every other one is squiggly. So how many layers of phospholipids do I have now? 2. So they call that a bilayer. So I just made a phospholipid bilayer. Makes sense. It's a bilayer, 2 layers of phospholipids. So I've got a phospholipid bilayer. Where do we find phospholipid bilayers? Cell membranes. Cell membranes are made out of phospholipid bilayers. So let's say that I've got these phospholipid bilayers. Let me get some blank paper. Okay, so here's my bottom layer of phospholipids. They call it the inner leaflet. And then this is the outer leaflet, if this is like the inside and outside of a cell. So this is my phospholipid layer, monolayer, monolayer. Now I've got a bilayer. Okay, so let's say I've got this bilayer, and it's floating on top of the water. Here it is. So we're floating in the water. Maybe I made phospholipid bilayer in the lake or something. I went out and I dumped it all in the lake. Now I'm floating in the lake. Here's my phospholipid bilayer. So what do phospholipid bilayers make up again? Yeah, the cell membrane. So our cells are made out of phospholipid bilayer. Okay, so now I dunk this underwater. So it was on the surface of the water, and I like smash my hand through the water, and now it's underneath the water, like this. One of these days, I'm just going to have like everything hooked up to like a chain. You know how people have like their keys? If you're at a motorcycle, you put your keys on a chain. I'm going to have like expo pins and stuff. I'll just be like, they'll be retractable. Because I don't want to look like a dork.
Didn't you have like an expo belt?
I do. You're like, where do you buy this? You don't. This is homemade from a previous student. I talked about how I needed an expo pin belt. And so last week of school, some of you seniors get all sentimental and stuff. You might give your teacher a $5 Starbucks card, maybe some hand sanitizer, and say, thanks, man. She stitched together an expo pin holder. And I had always said that I wanted it to be like, have you ever seen like people with an M60, how it's got like the bullets and they just strap it around their body like this, like Rambo? That's what I wanted, but she had not calculated for my massiveness, the fact that I'm swole, and so it wouldn't quite go, but it's supposed to go like this. So it's kind of too small for this, but then like too big for my waist. But it's still pretty awesome. Yeah, like Expo Man. The student made an Expo Man, Superman hero back there. So I do a lot of analogies with Expo pens, and so students make fun of me for it. But I say it's worth it because, I mean, Expo belt. So students will say, Mr. Cotton, you seem obsessed with Expo pens. I'll be like, no, my students are obsessed with Expo pens. I didn't make this. I didn't make Expo Man. I didn't make this. That's you guys. By the way, though, I go through a ton of Expo pens, so if you really are looking for something like at the end of the year for some appreciation, give me like a couple of Expo pens instead of Starbucks. Starbucks is good too. So I'm not asking for gifts, by the way. I was just saying. Never mind.
Mom, Mr. Cobb was begging for stuff at the end of the year. He was wanting a Starbucks sticker.
So let's say I've got this phospholipid bilayer. Remember, we're back at the lake. We're out there with Dale, the guy with scurvy. And he's probably at the lake. And so we're out at the lake, floating like that. We smash our hand through the water. Now the phospholipid bilayer is underwater, like this. So what happens next? It'll go back up. Before it goes back up, though, what will it do while it's still completely submerged? You're right. If it's less dense, kind of like this oil, it will go back and float on the top again. So I agree. But let's say that we slam it 20 feet under the water. So it's now 20 feet under the water. This is the level of the water. Oh, hang on. I almost drowned. So this is the level of the water, and it's down here. When it starts to float back up, what's wrong with the way that I have it floating back up right now? It's a sheet. What's unstable about this being a sheet? Like, which parts are unstable as a sheet underwater? Yeah, the tails on the edge are touching water. So what formation could they take to where they don't touch water? Yeah, a circle, a sphere. What shape are cells? Spheres. So what did we just make when we dunked this underwater? A cell. As long as cells contain and are surrounded by water, wait, aren't you 2/3 water? 3/4 water? Something like that? So as long as you're made of water, cells make themselves. So once I dunk this underwater, it folds up all the way around. So when this is underwater, I'll now have, oops, see, that's why I need a chain. Plus, I could be out somewhere and they're like, oh, you ride a bike? And I'm like, no, I've got a Honda, but like I'm a teacher. That's why I have all this stuff on my chains, because, I mean, it's obvious. So once I dunk this underwater, it automatically makes cells. Let me show you. Let's see. Being drug-free is my responsibility. Look, little bitty spheres. When I mix them together, they automatically make cells. Sorry, it smells like expired oil, but that's true. It might be better than the hand sanitizer. So they automatically, before it floats back up to the top, you just have a whole bunch of little bitty cells floating around in there. Now, it's not like we created life out of cooking oil.
That was vegetable oil.
It is.
So it's
So,
not phospholipid.
right, it's not really phospholipids. So we didn't really create life out of it, but if this was phospholipids, I just can't buy any. So if it was phospholipids, then those would be spheres made of phospholipid bilayer. So the point is still the same.
Why can't you buy phospholipids?
I don't know. I've just never seen them for sale. If you see any, tell you what, forget Expo pins or like a $5 Starbucks card. If you guys ever come across phospholipids, that would be an incredible present. Maybe I should start my own company of something the world needs is phospholipids. We could sell it at the Life store. We'll sell various amino acids and stuff too. Now, I'm not saying we just created life, because this is corn oil, and eventually it will float back to the top and separate out. My point is this. When you look at a phospholipid bilayer, and this is the part that like boggles my mind every time I say it in front of you guys. When I look at a phospholipid bilayer, it's 1/9,000th the thickness of a sheet of paper. So here's a piece of paper. It's 1/9,000th of the thickness of that. So if I had 9,000 phospholipid bilayers and I could stack them on top of each other, I can't because the phosphates would repel, but if I could stack 9,000 of them on top of each other, it would be that thick. Now, is that phospholipid bonded to his neighbor? No. Is he bonded to the guy across the hall from him? No. How thick is a phospholipid bilayer again? 1/9,000th the thickness of a sheet of paper. This is all that's holding me together. That's it. So imagine where am I hearing that? I thought I had an alarm. I have an alarm set for in a minute, but okay. You guys hear that, right? Is it coming from over here? No, my phone's right here. Hang on. Maybe my email is sending me an alarm about picking up textbooks. All right, I'm not sure. Okay, so the important thing is this. Imagine that I told you Timber Creek. Timber Creek is held together by bricks, let's say. The bricks are 1/9,000th the thickness of a sheet of paper, or maybe we let them be like an inch thick. Are those bricks bonded to each other? No. Is there any mortar or any cement between them? No. That's what holds the walls together. Are phospholipids more liquidy or more solid? They're liquid. They're supposed to be about as liquidy as olive oil. If you have pure phospholipid bilayer, it's supposed to be about as liquidy as olive oil. So here's my point. I'm made of about 100 trillion cells. Each one is being encased in a phospholipid bilayer that's 1/9,000th the thickness of a sheet of paper. It's liquid, and each phospholipid is not bonded with its neighbors. And the only reason that I don't fall apart is because the center never wants to touch water. And I'm made of water. That's all that's holding you together. Like this is all underwater. So back to my analogy of being out at the lake with Dale. Phospholipid bilayer. When I dunk this underwater and it folds, what's in the middle of it now? Water, because if I have my hand on the surface of water and I put it underneath and I go like that, I've got a handful of water. What am I surrounded by if I'm underwater? Water. So I have water on the inside, water on the outside. Are these phosphate heads okay touching water? Yes. What about the lipid tails? No. So when one of these phospholipids tries to squeeze out, so here's some phospholipids. 1, 2, 3, 1, 2, 3. When one of these guys tries to squeeze out, the water doesn't like that lipid tail, so it pushes them back in. And that's all that holds you together. So imagine if I built Timber Creek, like I was saying, back to the brick analogy. We have bricks. How thick are they? Really thin. Are they solid? No, they're liquid. Are they bonded to each other? No. And that's what holds us together. So the thing that's holding us together is the fact that the center of our phospholipid bilayer doesn't want to touch water, and that's it. Otherwise, these things would just fly off on their own. Just sort of bizarre if you think about it. It's liquidy so that I can do this and not shatter. Otherwise, if it was solid, I would have just broke myself. So it's liquidy. So right now, I'm pushing on that, and it's just going back, kind of like this. If I move this around, it just goes back where it was. So my phospholipids are being smashed, and then they just pop right back out where they were. Super weird. I find it weird. You might find it completely normal. You might be like, I knew we were made out of a layer of oil, 1/9,000th the thickness of a piece of paper, and that none of it was bonded with anything else. This is normal. All right, one last thing, and then we're going to leave to get our textbooks here pretty soon. Actually, we leave it 1:17, so we got just a little bit longer. The phospholipids on the inside and outside are typically different. This is a cool trick. So let's say I'm a cell, and let's say I'm infected with SARS-CoV-2 that causes COVID-19. You know what I'm supposed to do? I'm supposed to tell on myself and let you kill me. So let's say that we are all Mr. Cotton cells. Or let's say that you guys are white blood cells. You're immune cells. And I'm a Mr. Cotton lung cell. You're a Mr. Cotton immune cell. So Mr. Cotton immune cells, they don't know They don't identify SARS or HIV or E. coli. They just know it's not Mr. Cotton. So you guys basically go around and you check every cell in my body to see if it's a Mr. Cotton cell. You basically know all the proteins that Mr. Cotton has. And if something shows up that you don't recognize, you just kill it. It's almost like we're team at Timber Creek. And so anybody wearing purple, you're like, that's a falcon. Purple and gold, that's on my team. If you run into something green, you just kill it. If you run into something red, you just kill it. You aren't like, is that a Carol Dragon? Is it Keller High? You're like, I don't care, just kill it. So I run over anybody that's not wearing purple and gold. That's how your immune system works. It knows itself, and it attacks anything else. Occasionally, your immune system does something stupid and gets all pissed off at like peanut butter or something. And so now you have this giant reaction, this giant allergic reaction that could be deadly because you ate some peanut butter. Me, I had allergies. I had to give myself allergy shots when I was a kid. Times are different back then. So you could be like 12 and they'd be like, all right, here's this stuff. I'm not making this up. This is how medicine was. Maybe it's just because I'm from Oklahoma. Here's your allergy medicine. Here's a bunch of syringes. Every Wednesday, go over to the wall, mash your tricep up there a little bit, give yourself a shot. If something feels weird, give us a call. How do we dispose of all of these syringes? If you got liquid Tide or something like that at home that you wash your clothes in, yeah, take the hard bottle, and whenever you're done with the bottle, just throw them in there and put them in the trash. So that's what I did. You know what one of my allergies was? Cottonwood tree pollen. How's that for irony? So the point that I was wanting to make is, let's say that I'm a Mr. Cotton lung cell, and I'm infected with some sort of virus or whatever. One of the ways that I can tell on myself so that you can kill me, because otherwise I become like a SARS-CoV-2 factory. When viruses infect cells, that cell now becomes a virus factory. If I get invaded with HIV or hepatitis or SARS or the flu, I become a flu factory or a COVID-19 factory. So one thing that I can do, I'm not making this up, there's an enzyme called flipase. And what flipase does is it will flip some of your interior phospholipids to the outside. So now all of a sudden I'll take this blue one and put it on the outside. And then when you guys, my white blood cells, come along, you're like, that's not supposed to be there. Kill them. And that's how I tell on myself, just by flipping phospholipids around. Unfortunately, some viruses disable that enzyme. So now I'm unable to tell on myself, so they can go on and succeed in making the cell a virus factory. Super weird, isn't it? Okay, 1 or 2 pictures. Yeah, we're supposed to leave at 17-ish. Okay, so we'll look at 1 or 2 pictures, and then we'll be done for the day. If you look at this picture, come on, cursor, there you go. If you look at this picture, this gives you an idea of how thin a phospholipid is. So this is a cell under a microscope. Keep in mind, I am 100 trillion cells. The anatomy and physiology textbook that you guys use, there's 2 versions. The more hardcore version says that a cubic millimeter of human tissue has about 1 billion cells. That's how small cells are. Here's how zoomed in we are on this cell. This cell is a sphere. So if the edge of the cell is that big and I kind of complete the circle, isn't this cell like that big? You know what I mean? So that's how zoomed in we are, and that's the phospholipid bilayer. So if a cell is 5 feet tall, the phospholipid bilayer is 1 inch. And that's what's holding you together. Because you're made primarily of water. And that middle doesn't want to touch water. The last picture we'll see is this one. Phospholipids move left to right all the time. So they're just shuffling like this. Let's say this is my bottom layer of phospholipids. All the phosphate heads are pointing down, the pin caps. And this is my top layer. They're just shuffling around like this. Now, I can go and find it. It's in my pink cell biology book back there, that bright pink one. So I can find the exact numbers. But some dude measured how often do these switch. He basically shot a laser at a specific spot and looked at how many times does a new phospholipid enter and exit that spot. Almost like this. Pretend that we're playing like musical chairs. And let's say I put a mirror on this chair and I shoot a laser at it. So as long as nobody's sitting there, the laser bounces back, right? It reflects back. And you'll be like, oh, the laser's coming back. If I sit on it, then now all of a sudden the laser doesn't bounce back, right? That's essentially what they did. And I'll have to look up the numbers, but it was something like 10 million times. The average phospholipid moves, like the average spot has 10 million different phospholipids in it in a given second. They're moving that much. So it's like musical chairs, and it's like 1, 2, 3. Only, it's almost exactly like that, except it's 10 million times in a second. That's how much they move left to right. So that's what they mean when they say frequent. The flip-flop is rare. They measured the flip-flop, and it's on the course of like every 3 weeks. So every 3 weeks, one of these guys will migrate to the other side temporarily and then flip back. Hopefully before the cell gets killed. Otherwise, we accidentally kill cells. We're just like, oh, whoops, sorry. Blew up the wrong cell. All right, we got to go and get textbooks. So for you guys on the Zoom, see you later. In the chat, I tell you how to get textbooks. But otherwise, you guys are free to go. I'll paste that in there one more time. But that's it. Thanks for coming. All right.